Welcome to Lecture 1B entitled Lines, Planes, and Surfaces. This is the second in a sequence of 4 lectures constituting Lecture 1. And so the first slide, as usual, gives you indication of what the objectives are and also the location from which the material has come from. So this is from section 13.5 of the textbook and sections 4 and 5 of Reading Assignment 0. And just a general note that sections 4 and 5 of Reading Assignment 0 discuss geometric metrics such as length, area, and volume, and coordinate and vector component transformations, and these we will refer to later in the course. And so we're looking in this lecture at the properties of planes and lines. Some of this you may have been exposed to in first year, but we'll just add a little bit more substance to whatever you learned last year, and also introduce you to the next topic that we'll be covering in Lecture 1C, and that is coordinate transformations and basis vectors in other coordinate systems. And in order to help us understand that, I need to understand how we can basically establish points in a given space by the intersection of n-1 dimensional objects. All right, so this is again the second slide, which is typically the outline, and I'm not going to dwell on it. You can look at it. This is the material we'll be covering in the subsequent slides. So as an example, we have planes and lines in 3D. We will be looking at 2 types of surfaces. One would be a surface which is planar, and one which is a curved surface. We'll be dealing with curved surfaces later in this course, but for the time being, we're interested only in planes in 3D, which we can extend to higher dimensions. And this material can be found in chapter 13.5. So these 2 diagrams here show, for instance, an example of a plane. That's a surface. And here basically we're showing a curved surface. We also are showing 2 vectors here, and so because this is a surface in 3D, means that we can rotate and translate this surface. And so how do we distinguish between different orientations of a surface? Well, we basically define an orientation vector, which is normal to the surface at any given point. If you were to basically look at the vector normal to a surface, a planar surface at any point, it'd be pointing in the same direction as shown here. Now there is an ambiguity here because the surface basically has a top and a bottom. So in fact, the orientation vector could be either pointing outwards from the surface or downwards from the surface. Depending on the nature of the problem, there will be some reference given with respect to the direction in which the orientation vector should be pointing. Otherwise, basically, it's left to the user to decide which direction they want to choose. All right, so one of the defining characteristics of an equation of a plane is that it's linear in the variables x, y, and z. And so what you have is a constant coefficient times x plus a constant coefficient times y plus a constant coefficient times z is equal to a coefficient d. It turns out that the orientation vector, right, is nothing more than the constant coefficients of each one of these variables. So if you put this into an ordered triplet, then ABC corresponds to the orientation vector, or alternatively, multiplying this vector by -1, which would give you minus a minus b minus c, is an alternate form of the orientation vector. So this vector, if a, b, and c are positive constants, would be pointing upwards and outwards, whereas this one would be pointing downwards. So for example, in this example shown here, the a would be 1, b would be 1, and c would be 1. Alternatively, if you want the vector to point in the opposite direction, then these just take on negative values, which is the orientation vector that you see here. Now we can extend this concept to higher dimensions. That is, a plane in 4D we would call a hyperplane. Again, it would be linear in terms of the variables of the system. There are going to be 4 variables now if we're dealing with a 4-dimensional systems, x, y, z, and w. And you have constant coefficients for each one of these, equaling e. If you wanted an orientation vector for this in 4 dimensions, then the ordered quadruplet would be A, B, C, and D. Alternatively, it could be pointing in the opposite direction, so this would end being multiplied by -1. Now for curved surfaces, as an example shown here, the orientation vector will depend on where you are on the surface. So for example here, and we'll be showing this later on in the course in terms of how this orientation vector is derived, but in this case, the orientation vector depends on the position x, the position y, and the value of z is basically taken to be 1. Now again, because the surface can be outside or inside, then a vector which is pointing in the opposite direction is also an orientation vector. And so the problem statement must somehow suggest which one of these orientations is the one that should be chosen. Otherwise, there's a level of ambiguity. So if you want to look at, for instance, these 2 examples in terms of a demonstration, then you can go to this URL here and click on it. You'll basically be able to play with the orientation of this particular plane here. You can look at it from different angles, see for yourself that, what this looks like. Or alternatively, if you're interested in looking at how does the orientation vector change as you move to different points on the surface, then that can easily be done by changing the value of x in this variable slider and changing variable y, and then watching how this orientation vector changes. And all of this can be obtained again from this particular link that you see here. All right, so let's look at 3 different examples involving planes and lines in some combination. So this particular example I've given here is example 6 from chapter 13.5. What is the equation of a plane given 3 points in 3D space? So you're given a point O, a point Q, and a point R, each having specific coordinates. On the right, you basically see a visual indication of the plane that we're going to basically derive. And so the blue rectangular area is the plane. And then the specific other vectors that you see there, I'll basically refer to as we walk through this slide. The vector n is basically not to scale, and it's not a unit vector. Normally we choose n to represent a unit vector. In this case, it's not. Okay, so we want to find the orientation, which is a vector of the plane. All right, so how do we start? So we know that 2 points or 3 points can basically, when you connect the points together, they will lie in a plane. All right, and so what you can do is to say, construct any 2 vectors. In this case, there are 3 possible vectors to choose: OQ, OR, or QR, or the reverse. It doesn't matter. So if we take any 2 vectors, and I've chosen OQ and OR, and you obtain that in vector by basically subtracting the Q coordinate, the O coordinate from the Q coordinate to produce the vector OQ. And if you want the OR vector, basically you subtract the components of the O vector from the R vector. And so those basically are indicated here. All right, so the vector that's normal to a plane, right, can be obtained by using a cross product. We know that if we take any 2 lines, which we know are going to lie in the plane, then the vector normal to the plane in which those 2 lines, right, can be obtained by taking the cross product. And so that's exactly what I've done here. Put it into determinant form, make the substitutions. Second row is for OQ, third row is for OR. You do the computation, which is just a determinant of that matrix, and you'll end up with an n vector, which is 10, 8, and 10. Next step is to create an arbitrary vector with its head at some arbitrary point x, y, z in space, and its origin at the position O. All right, and the position O is already defined. I've chosen O, could have been basically other combinations depending on how you set up the problem. In this case, I've set up as O. And I want to create another vector now, which has got its tail located at the origin. And so OP would be just subtracting the two components. That's x minus 2, y plus 1, z minus 3. All right, so that's an arbitrary vector. All right, so that vector needs to lie on the plane on which the lines OQ and OR lie. So how can we enforce that condition? We can enforce it by essentially imposing the constraint of orthogonality. So if I take the dot product of OP and N and set it to 0, that guarantees that the vector OP is perpendicular to the normal of the plane. Okay, so that OP would be lying in the plane. So I just take the dot product, follow through, and set it to 0. And then after some rearrangement, because after all, the dot product produces a scalar value, you end up with an equation 5x plus 4y plus 5z equals 21. And this is the equation of the plane. So if you look at the diagram on the right, I've labeled everything there. So OR, OQ, OP, O is the actual position, which we chose as our origin for this particular problem, and N. And so all the basic quantities of interest are on this diagram. All right, so let's look at another example, the equation of a plane given that two lines intersect. And this is example 9 from chapter 13.5. Now there is a diagram on the right, basically to sort of complement the discussion on the left. And all the vectors that I've shown there, also vectors that lie along lines, the OP and OQ in particular. So for instance, for line 1, we have to parameterize line in terms of some variable. And we use two different variables because we're dealing with two different lines. So you're given the first line 1, which is parameterized as shown. And we're basically calling that line OP. And line 2 is parameterized with the variable s. And so it has a particular form. All right, and so what we're interested in is what is the intersection point between those two lines. And so the way you obtain that intersection point is you equate the x components of line 1 and 2, y components, and z components, which is what I've done when you look at the section that's labeled in green. So simplifying for the x component, you get 2s minus 2 equals t. Simplifying for the y component, it's 2t plus 1 equals 2s minus 1. Simplifying for the z component, 3t plus 4 equals 3s plus 1. And then basically just simplifying those equations, you'll see the final result in yellow. Now you notice there's some redundancy because the second and third equation are identical, which means you only need to use one of them. So ultimately what you end up with are two equations and two unknowns, and you solve. So the solution for those two equations, which are these here, is s equals 1 and t equals 0. So if you substitute in for s equals 1 and t equals 0, you can basically establish what the intersection point is, and that would be 0, 1, 4. You can either substitute basically an equation involving the first line or the second line. It really doesn't matter. Okay, so we have basically then intersection point. So now what we need to do is produce two additional points, one on each line, so that we can generate a vector between the intersection point and an arbitrary point on line OP and an arbitrary point on line OQ. And so we basically just choose an arbitrary value for s, substitute in this case it's 0, and we end up with a point Q, minus 2, minus 1, 1. And for the second line, just choose an arbitrary value for t equals 1, and you end up with a point P, 1, 3, and 7. All right, and now we also produce an arbitrary point, create an arbitrary point R at some arbitrary location x, y, z. This is the one which we'll be using to basically establish the equation of the plane. All right, so we have to now generate a number of vectors. So we have the vectors between the intersection point 0 and points Q, point P, and point R. So you have three different vectors that we're going to create here. So OQ basically you can obtain, since we know what O is, we know what Q is, we can obtain a resultant. Similar for OP. And for OR, the only difference here is that R has basically arbitrary values for X, Y, and Z component. Hence, we basically just said X, Y, and Z. And so we have our three main vectors. All right, so what is the orientation of vector of a plane going to be? Well, you've got OP and OQ. They intersect, but those two lines lie on a plane. So if you take their cross product, it'll give you a vector basically that's pointing perpendicular to the plane in which OP and OQ lie. And so that's what I've shown there, O minus 3 and 2. That's the resultant. All right, what's the equation of a plane going to be? Again, we impose the orthogonality constraint. You take the dot product between this arbitrary vector OR, OS, which is normal to the plane, and we want OR to lie in the plane. Therefore, the angle between those two vectors must be 90, which means their dot product is equal to 0. Work it out. It's a scalar equation. And the resultant after simplification just becomes minus 3y plus 2z equals 5, which is the equation of the plane in which the two intersecting lines lie. And again, if you wish, you can click on this link and you can manipulate this particular plane, look at the different vectors. It's shown here as orange, but in actual fact, the color will vary depending on the orientation as you move it around. So that's just the way the problem was set up originally. Okay, so the next thing is to look at equation of a line formed by the intersection of two planes. So if you intersect two planes, you'll always end up with a line. And this is question 73 from chapter 13.5. So we're given two planes, plane Q and plane R, which is at the top of the page. We can establish the orientation vector for each plane. Again, you just pull off the prefix to the variables and you create the orientation vector for plane Q and the orientation vector for plane R. The vector that's perpendicular to the two orientation vectors, NQ and NR, can then be obtained. So we just take the cross product and we end up with the resultant value. That's 1, 2, and minus 3. And this is in the direction of the line of intersection. Okay, you can show that quite simply, that it'll be in the direction of line of intersection. And looking at the video, the interactive simulation on the right, you can play with it to show that that is in fact the case. So we know it's in the direction of the line of intersection. All right, so now basically what we'd like to do is we want to know what the equation of that line is. So we need a reference point. So we need to start with some arbitrary point on the line of intersection. And we'll call that point O. And we obtain that by equating the equations for the two planes. That is minus x plus 2y plus z equals 1 and x plus y plus z equals 0. Right? And then what we do is express y and z as a function of x and then choose a value for x. Now you can actually change that around. It doesn't have to be express y and z as a function of x. It could have been any combination you wish. It's somewhat arbitrary. It really doesn't matter. So it's your choice. So if you solve these two equations, in the case of y as a function of x, you get y equals 1 plus 2x. And if you solve as a function of z, you get minus 1 and minus 3x. And so now you choose some arbitrary value of x, which then gives you the value of y and z. We've chosen here x equals 0. And so we obtain a point 0, which is 0, 1, and minus 1. Some position on the line of intersection. All right, so now we need to create a vector, and we would like that vector eventually to be parallel to that line of intersection. So we start with an arbitrary vector x, y, z, right? And we take the position of the O1 minus 1, subtract the two, and we end up basically with a line that's parallel to the intersection line, right? And so what we do is to realize that if we have a vector that's parallel to the intersection line, and we know the direction of that intersection line because it's been pre-computed with ns, then any linear scalar factor with respect to ns will be equivalent to that vector. And so we've chosen t to be this scalar value. So if you basically solve this equation, you're basically solving for the x component, the y component, and the z component. For the x component, you're going to have x equals t, the y component 1 plus 2t, and the z component would be minus 1 minus 3, 2. And these would be the coordinates of the point on that line, intersection line. Now you can either write it this way, or you could also write it in terms of a position vector. In terms of position vector, you would just put the x, y, and z components, but you use an angular bracket instead. And again, t being the value that can range anywhere between minus infinity and plus infinity. And so that position vector would be sweeping out the line, that is the intersection line. If you look on the right now, you can sort of see the description, what the red plane is. It actually doesn't show up as red here. That's the plane Q, the blue plane is plane R, and the black line is the intersection line. And NS, NQ, and NR, again, are not to scale and not unit vectors. Okay, so the next topic of interest is the intersection of n-1 dimensional objects. And we start by saying n equals 2. N equals 2 would refer to basically a 2D problem, which means we're looking at a plane. And this material comes from reading assignment 0, sections 4 and 5. So n equals 2 implies a 2D surface. That means objects with dimensions n-1 are lines or curves in 2D space. So plugging in 2 gives you 2 minus 1. One-dimensional object is a line or a curve. Any point in 2D space is obtained from the intersection of two lines or curves with the direction of the tangent for each line or curve aligned with a basis vector. Okay, this would be a basis vector at a given location. In our case, we're always going to be using orthonormal basis vectors, which means the vectors are all orthogonal to each other and they're unit vectors. Okay, and you might ask the question, what is the direction of the orthonormal basis vectors? Because I basically arbitrarily making them point in a specific direction. Well, everywhere throughout this course, we'll be applying the right-hand rule, which means the direction is assigned by convention. We'll discuss this in more detail in the next lecture, which is lecture 1C. So let's look at the two examples below, one for Cartesian coordinates and one for polar coordinates. For Cartesian coordinates, basically, we have one line that's parallel to the x-axis and one that's parallel to the y-axis. And you have basically these two lines will intersect, and the point of intersection is a particular point. If you move the lines up and down or left and right, you can map out as many points as you wish. As far as the unit vector is concerned, the orthonormal vectors in this case will be perpendicular, right? And you can see this generally speaking. So if we have a vector which is parallel to the blue line and a vector is parallel to the red line, you can see these two lines also being perpendicular to the individual lines. And the y-hat axis at a given point is pointing up and the x-hat axis is pointing to the right. If you move those lines back and forth in any direction, the y-hat axis and the x-hat axis do not change orientation. And so that's a very special property of Cartesian coordinates. This is not the case if you move to polar coordinates. In polar coordinates, you typically define a new coordinate variable r and theta. And r base is a radial vector. It starts at 0 and moves outwards in a radial direction to infinity. Theta is measured in a circumferential direction. Again, because of the right-hand rule, we choose to always map it in such a way that it's going counterclockwise, looking onto the xy plane. And so here now we're dealing with lines. So in one case we hold r fixed, in the other case we're holding theta fixed. So if we hold theta fixed, then x and y basically change depending on the value of r, which is the blue line you see, that's a radial line. On the other hand, if we hold r fixed, which is basically the red circle, and you vary theta from 0 to 2 pi, you're mapping out the whole circle. Okay? Now, the tangent to the red circle and the tangent to the blue line, basically, at a given point where the two lines intersect, are the basis vectors that we're interested in. So we have a basis vector that's basically tangent to the circle at the position shown in black. We call that theta hat. It's a unit vector. And then there's a vector perpendicular to that surface in a radial direction, which is r hat. Right? Now, the interesting thing here is, if you, for instance, increase the radius of the circle or move the line so that its angle theta is different, then you'll find that the direction of theta hat and r hat on xy plane will change depending on the location. And that is something you'll immediately see as soon as you're dealing with curvilinear coordinates. Not the case with Cartesian coordinates. All right, so the next thing to do is to look at, well, what happens if we increase the dimension to n equals 3? N equals 3 would imply a volume. So let's do that. So in this case, it's a volume. That means objects with dimension n minus 1 are actually surfaces in 3D. But they are oriented surfaces because they have a direction, okay? If it were a surface in 2D, there is only one surface. So these are oriented. Any point in 3D space is obtained from the intersection of three surfaces. We will call these traces. We'll discuss that in the fourth lecture. So the orientation vectors in 3. The orientation vector for each surface is aligned with the basis vector. Again, we're talking about orthonormal basis vectors in our examples. And the direction of the orthonormal basis vectors will be consistent with the right-hand rule, as will be discussed in Lecture 1C. So let's go and look at three different examples, starting with the Cartesian coordinates. So if we take basically three different surfaces, again, we would basically hold one coordinate fixed, and that means the other two are free to move. So if we hold z fixed at some value, then we're basically dealing with something parallel to the xy plane. If we hold the value of x fixed, then we're dealing with something that's parallel to the zy plane. And if we basically hold y fixed, then we're dealing with something that's parallel to the xz plane. So you can move those planes up or down, left to right, front to back, and the intersection of those three planes will be a point that will be moving depending on how the planes are being moved. Now, if you take a vector that's perpendicular to each one of those surfaces at the point of intersection, those will be the basis vectors at that location, and those are shown in black on the left. If I move those surfaces in all possible directions, I'll find that the z-hat direction, the y-hat, and the x-hat do not change independent of position. Again, that's a property of Cartesian coordinates. That's not the case if we move to either cylindrical coordinates or spherical coordinates. So in cylindrical coordinates, basically we're given a transformation, x equals r cos theta, y equals r sine theta, and z is not changed, and it remains unchanged. R is greater than or equal to 0, and 0 is less than or equal to theta is less than or equal to 2 pi. Theta is an angle basically measured on the xy plane. So how do we get the three surfaces? Well, we basically say for one surface, you hold r fixed. For another surface, you hold theta fixed. And for a third surface, you hold z fixed. If we hold r fixed, okay, if we hold r fixed, that means theta can vary and z can vary, in which case we're looking at this red half plane. On the other hand, if we hold z fixed, right, that means r can vary and the theta can vary, right? That means we're dealing with this plane, this gray area. So the other case would be basically if we hold theta fixed, and we hold, if we hold r fixed, right, some value, some specific value, then what we're mapping out is a circle. So theta can go from 0 to 2 pi, and z can be any value you want, so it's an infinitely long cylinder. So that's how we basically create these three different surfaces. And again, the vectors are pointing perpendicular to the surfaces, so the r hat vector is pointing this way, theta hat's pointing this way, and z hat's pointing this way. Clearly, if we basically start moving these surfaces around, we're going to basically change the position of the intersection point, but at the same time, the direction vectors, these basis vectors, are going to be pointing in different directions when you look at it in terms of the x, y, z space. In spherical coordinates, the situation would be a transformation involving rho, theta, and phi. Phi is measured with respect to z-axis going down. Theta is still measured in the azimuthal plane, the xy plane.
And the range on rho is greater than 0, range of theta from 0 to 2 pi, and the range on phi would be from 0 to pi. So again, going through the same arguments, we basically would in one case hold rho at a constant value, in which case, what are we doing? We're mapping out a sphere of a specific radius. If we hold theta fixed, right, and change rho and phi, then we're mapping this half plane. If we hold phi fixed, that's an angle phi with respect to z-axis, then we're mapping out this cone. You change the angle phi, you change the angle of inclination of the cone. So these are the three different surfaces that we're dealing with. And the unit vectors, orthonormal basis vectors, will be perpendicular to the surfaces at the point at which the intersection between the three surfaces occurs. So you can see the phi hat vector, the theta hat vector, and the rho hat vector. Clearly, if you increase the radius or move the half plane or change the angle of inclination of the cone, the intersection point will move. But in the process of having the intersection point move, the direction of the orthonormal basis vectors will also change direction with respect to XYZ space. So effectively, this is again a property of curvilinear coordinates. Depending on where you are, the unit vectors are pointing in a different direction. So that more or less concludes Lecture 1B. Thank you for listening.